Half the rooms in a typical American home receive zero natural daylight. Not dim light. Zero. And for most of history, if a room didn't sit on the outer wall of a building, that was simply the cost of living inside it. But there is a device, installed on roughly 2.5 million American homes right now, that can flood any interior room with full-spectrum sunlight. No window. No skylight. No opening to the outside air. Under independent testing, one version of this system cut lighting energy use in a windowless room by 69%. And most homeowners have never heard of it. If you find this kind of overlooked engineering useful, subscribe. We cover forgotten technologies and hidden infrastructure every week. The fundamental challenge of interior daylighting has existed for as long as people have built enclosed structures. Windows solve the problem for perimeter rooms. But bathrooms, hallways, laundry rooms, walk-in closets, and interior kitchens sit in the middle of a floor plan, surrounded by other rooms. There is no exterior wall to put a window in. The standard solution for the past century has been to run electricity to those spaces and leave the light on. In a single windowless bathroom with a 100-watt equivalent bulb running 10 hours a day, that adds up to roughly 365 kilowatt-hours per year, and zero connection to the circadian rhythms that natural light supports. The workaround that existed before sun tunnels, the conventional skylight, solved the location problem but introduced a set of new ones. Flat glass skylights leak at the frame. They allow substantial heat loss in winter. In summer, they transmit infrared radiation directly into the room below, raising air conditioning load. And they require the room to be directly below the roof, which limits their use to single-story spaces or the top floor. By the late 20th century, the basic geometry of the skylight had not changed in any meaningful way since the Romans had solved the same problem. It was still just a hole in the roof with glass over it. The history of intentional daylighting goes back at least 3,500 years. Around 1500 BCE, Egyptian architects cut narrow vertical slits high into the stone walls of the hypostyle hall at Karnak. These are clerestory windows, not for ventilation, but engineered to throw controlled daylight onto specific columns at specific times of day. The geometry was deliberate. In the 2nd century CE, the architects of the Roman Pantheon took a different approach. They left a single 30-foot circular opening at the apex of the dome, the oculus. It serves as light source and sundial simultaneously. The beam of light it casts tracks across the interior through the year, marking time with precision the Romans built into the structure intentionally. For the next 2,000 years, the fundamental answer to interior daylighting remained the same: cut a hole, put glass over it, accept the consequences. Gothic architects stacked clerestory windows to flood nave interiors. Industrial-era factories used sawtooth rooflines to catch north light. The 20th century gave us the flat glass skylight. Each was a variation on the same principle. In 1986, an Australian inventor named Steve Sutton began working on a different geometry entirely. Rather than cutting a large opening above the target room, Sutton proposed a small transparent dome on the roof, connected by a polished reflective tube to a frosted diffuser at ceiling level. The basic concept had been attempted in various forms before. Light pipes had been studied in industrial contexts, but Sutton was the first to engineer it into a practical, manufacturable residential product. The system has 3 components. A dome on the roof. A reflective tube through the attic. And a diffuser at ceiling level. Each does a specific job. The dome is not just a weather cover. Its curvature means it intercepts low-angle light, early morning, late afternoon, winter sun, that a flat skylight would largely miss. When the sun hits the dome at 15 or 20 degrees above the horizon, it bends that light downward into the tube. This is significant in winter months at high latitudes, when low sun angles would otherwise make a flat skylight nearly useless for most of the day. Below the dome, the light enters the tube. The interior surface of a premium tube is coated with a material called Spectralite Infinity, which reflects 99.7% of visible light at every contact point. That number matters because of how many times the light bounces on its way from roof to ceiling. A typical residential installation requires roughly 10 reflections. After 10 bounces at 99.7%, 97% of the original light arrives at the diffuser. The light has lost less energy traversing the entire tube than it would crossing a single pane of double-glazed glass. Budget tubes use standard aluminum, which reflects 95%. After 10 bounces at 95%, only 60% of the original light arrives. That 40-point difference is visible to the naked eye in any side-by-side comparison. The more counterintuitive feature of the system is thermal. The same reflective coating that bounces visible light is engineered to absorb infrared, the wavelengths that carry heat energy. With each reflection, more than half of the remaining infrared is absorbed by the tube wall and dissipated into the attic space. By the time the light beam reaches the diffuser, it has been stripped of most of its heat load. The room below receives high-quality visible light without the solar heat gain that makes conventional skylights a burden in warm climates. At the bottom of the tube sits the diffuser, a frosted lens or prismatic panel that scatters the concentrated beam evenly across the room. The result looks and performs like a ceiling-mounted electric light fixture. It is, in fact, a column of filtered sunlight. The performance data for these systems comes from controlled research, not manufacturer literature. Researchers at Lawrence Berkeley National Laboratory measured annual lighting energy reduction in real installations. A 14-inch tube reduced lighting energy use by 22 to 32% annually. A 22-inch tube, in the same study, reduced it by 27 to 69% depending on orientation and latitude. A national grocery chain installed 164 solitube units across a 43,000 square foot supermarket in Chino Hills, California. During peak daylight hours, the tubes provide nearly all interior illumination. The building's electric lighting load during daytime hours dropped close to zero. Sunnybrook Hospital in Toronto approached the technology from a different angle entirely. Clinical research had established that exposure to natural daylight stabilizes circadian rhythms and correlates with shorter patient recovery times. The hospital installed tubular daylighting systems in patient recovery wards on that basis. Over 1,800 sun tunnel units are now installed in medical facilities across 40 countries. Against a traditional skylight, the financial case is straightforward. A professionally installed sun tunnel runs $600 to $1,300 per unit. A comparable traditional skylight costs $1,600 to $4,200 installed. The sun tunnel runs 60 to 80% cheaper. The solar heat gain coefficient of a sun tunnel, a measure of how much solar heat it emits, sits around 0.2. A standard skylight ranges from 0.3 to 0.5. Lower SHGC means lower air conditioning load in summer. 2.5 million sun tunnels are installed in the United States today. That number sounds large until you consider there are approximately 145 million housing units in the country. Penetration is well under 2%. The reasons are not technical. The first barrier is awareness. Industry surveys consistently find that over 60% of American consumers cannot identify what a tubular daylighting device is or how it differs from a skylight. The product is not marketed through television or mainstream retail. It lives in the catalogs of specialty contractors and the back shelves of building supply stores, found mostly by people who went looking for it. The second barrier is upfront cost relative to perceived priority. Even at 60 to 80% cheaper than a traditional skylight, an installed unit runs $600 to $1,300. Most homeowners working from a fixed remodel budget are replacing appliances, fixtures, or flooring. A ceiling penetration for a room that already has an electric light is rarely the first item on the list. The third barrier is the one most likely to produce a bad outcome if ignored: installation quality. A correctly installed tube will not leak. A tube with poor flashing at the roof collar, or one running through an uninsulated attic in a humid climate, will accumulate condensation that drips from the ceiling diffuser and looks exactly like a water leak. The product must be installed correctly, by someone who understands roof flashing and attic ventilation, or it creates precisely the problem it was designed to avoid. This is not a design flaw. It is a trade-off that requires competent installation. The practical decision tree for a sun tunnel installation starts with being honest about what the device does and does not do. It is not a window replacement. It offers no view, does not open, and does not ventilate. If the choice is between a window and a sun tunnel for the same wall, choose the window. If the choice is between a sun tunnel and an electric bulb in a windowless interior room, the sun tunnel is the better long-term answer. A 10-inch tube covers up to 150 square feet, a hallway, walk-in closet, or small bathroom. A 14-inch tube covers 200 to 300 square feet, appropriate for a kitchen, bedroom, or laundry room. An 18-inch tube covers 350 to 500 square feet, enough for a great room or open-plan living area. As a rough calibration, a 14-inch tube at midday delivers light equivalent to 5 100-watt incandescent bulbs. Orientation is as important as size. In the northern hemisphere, a south-facing roof slope collects substantially more daylight than a north-facing slope, particularly in winter when the sun tracks low across the southern sky. East and west slopes deliver strong morning and afternoon performance respectively but lose midday output. Where a south-facing, unobstructed slope is available, that is where the tube belongs. Cost splits into 3 tiers. A DIY kit runs $300 to $900 all in, assuming basic tools. Professional installation on a standard asphalt shingle roof runs $600 to $1,300 including parts, labor, and flashing. Specialty roof materials, clay tile, standing seam metal, slate, will cost more. In every case, the total is well below the $1,600 to $4,200 a traditional skylight costs. 2 practical constraints govern every installation. First, run length. A 10-inch tube should not exceed 20 feet of total length, and a 14-inch tube should not exceed 30 feet. Beyond those lengths, cumulative reflection losses reduce delivered light meaningfully. Second, path clarity. Each 90-degree elbow in the tube costs a measurable amount of light. Dense attics with significant HVAC ducting or structural framing make the system less effective and may require a larger tube to compensate. On the regulatory side, California's Title 24 Building Code offers an explicit exemption that favors tubular daylighting devices over conventional skylights in efficiency calculations. California, Florida, and Arizona have passed solar rights laws that classify these devices as protected solar energy systems, overriding most local homeowner association restrictions that might otherwise block roof modifications. The sun tunnel is 40 years old. The problem it solves is 5,000 years old. Humans need natural daylight, and the rooms we actually spend most of our time in, bathrooms, hallways, interior kitchens, have never sat on the perimeter of our buildings. A polished metal tube and a curved dome can carry sunlight into rooms that windows will never reach. The engineering is not complicated. The materials are mature. The performance data is peer-reviewed. What the technology is not is a solution for every situation. It requires a clear roof slope, a reasonably unobstructed attic run, and competent installation. It works best in consistently sunny climates. In overcast climates at high latitudes, output drops in winter, though the dome's ability to catch low-angle light partially compensates. For self-sufficient households specifically, it eliminates a lighting circuit that would otherwise draw from battery storage or grid power for hours every day. A single 14-inch tube serving a windowless kitchen reduces the daily energy draw from that room by the equivalent of 5 light bulbs running all day. Multiplied across multiple interior spaces, that is a meaningful reduction in electrical load. The question is not whether the technology works. It does. The question is whether awareness will ever catch up to performance. At 2.5 million installations in a country with 145 million housing units, there is still a very large gap between what this technology can do and how many homes it currently serves. If you have an interior room that has never seen daylight, that gap might be worth examining. If you enjoyed this documentary, be sure to like, subscribe, and let us know what topic you'd like us to investigate next. And if you're interested in more forgotten technologies and hidden engineering solutions, check out the next video on your screen.